Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you have information about online seminars for exams PFM, IFM, and LTAM, and the study manuals for those exams that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here's the problem for today for exam LTAM. This is the last problem from the spring 2019 course LTAM examination, the written answer section. In a mortality study of a cohort of 12 80-year-olds, you are given the following observed exit times: 1 plus, 2, 2, 2 plus, 4, 4 plus, 5, 5 plus, 7, 8, 9 plus, and 9 plus, where plus indicates censoring. All other exits are deaths. Let S hat of t denote the Kaplan-Meier estimate of the time t survival probability, S of t, for a life age 80. Part A. Specify S hat of t for all values of t for t between 0 and 9, and hence show that S hat of 6 is equal to 0.60 to the nearest 0.01. You should calculate S hat of 6 to the nearest 0.001. Part B. Show that the estimated standard deviation of S hat of 6 using the Greenwood's formula is 0.16 to the nearest 0.01. You should calculate your value to the nearest 0.001. Calculate an approximate 95% linear confidence interval for S of 6. Calculate an approximate 95% log transparent confidence interval for S of 6. Part D. Explain why the log transparent confidence interval is preferred when estimating S of t. Part E. Suppose that you have a 13th observation truncated at time 3 and the right censored before time 4. Without further calculation, explain whether this would increase, decrease, or have no effect on your estimate of S of 6. For part A, we just write out the standard form of the estimator. So it's 1 before we have any observations. Then we just get it by multiplying out the expressions of the form 1 minus Si over Ri until we finish the count of all of them to the maximum time. And then we just multiply out all of them, 1 minus Si over Ri. That's the standard form of the Kaplan-Meier estimator. Well, this is the data in this study. And we calculate the RIs by taking the population minus the departures. And you can see them for I equal to 1, 2, 3, 4, 5, and the times, and the SIs, and then RIs. So here is the estimate of the survival function. It's 1 before the first observation, then it's 1 minus 2 over 11, so 9 over 11 after those 2 are accounted for. And then next one has 1 minus 1/8 multiplied by this 9 over 11 that we just established. And we just, at every point, we multiply the previous value of the survival function by 1 minus the appropriate fraction. And here are the numbers that we get. And in particular, S hat of 6 is 315 over 528. That's approximately 0.596591. This is 0.60 to the nearest 0.01. For part B, the Greenwood formula is actually provided in the standard ultimate life tables, and we calculate the the variance of s hat of 6 as s hat of 6 squared times 2 over 11 times 9 plus 1 over 8 times 7 plus 1 over 6 times 5, and this is approximately 0.0254101, and the square root of this is the standard deviation, approximately equal to 0.159405, or 0.16 to the nearest 0.01. For part C, part 1, an approximate 95% linear confidence interval for S of 6 is S hat of 6 plus minus 1.96 times the standard deviation we just calculated. And so we use the values we just calculated and get the estimate, which is from 0.284157 to 0.909025. While an approximate 95% log transfer confidence interval for S of 6 is S hat of 6 to the power 1 over u to S hat of 6 to the power u, where u is equal to e to the power 1.96 sigma S hat of 6 divided by S hat of 6 times the natural logarithm of S hat of 6. We plug in all the values. We get this u to be approximately 0.362805, and then 0.59659 to the power 1 over that to 0.59659 to that power is the confidence interval we're looking for, and that ends up being approximately 0.240823 to 0.8291114. For part D, the log transfer confidence interval is preferred when estimating S of t because it always produces an interval, n interval here, my apologies, within the 0-1 range. And of course, this survival function as probability has to be between 0 and 1. For part E, now we suppose that you have a 13th observation truncated at time 3 and right censored before time 4. The 13th observation will have no effect on the estimate of S of 6, as it does not change the deaths number and timing, or the risk set exposures at the observed times of death in this study. Please remember, this is copyrighted material. The problem itself belongs to a Society of Actuaries. The solution is mine. Good luck in your studies, and good luck on the test.